Okay, this problem says astronomers discover a planet orbiting a star similar to our sun that's 20 light years away. How fast must a rocket ship go if the round trip is to take no longer than 40 years in time for the astronauts aboard? So that would be the proper time for the astronauts aboard. How much time will the trip take as measured on Earth? Okay, so how much time will pass on Earth while those astronauts take the trip? Okay. Now, a couple of things. We've defined an interval as dx square plus dy square plus d square minus uh, d z square minus c square t square dt square. And this is the proper time that has passed between these two events. Okay. Now what we'll do is, as far as units go, we'll measure distances in light years, um, and so and okay, so let me use a different notation. We'll measure distances in light years, and so let's say it says light signal traveling, and this will be time in years. So this will be uh, light years. So let's say, and the speed of light in these units will be, so distance will be light years. Okay, actually, let me just, d is, and speed of light will be, light travels 1 light year in a year. So speed of light will be 1 in these units, t years. So the distance traveled in t years will be t light years. Okay, so those will be the units, and in these units c is 1. Also, so also if you wanted to calculate the proper time, so here's a space-time diagram ct. You saw that a light signal travels with along this path, light signal. Now any particle has a whirl line like that, and if you wanted to calculate the proper time spent by the particle between initial and final locations, what you do is you break this path into little intervals and integrate that, and this is equal to square root of minus ds squared. Okay, so that's how you would calculate the proper time spent by proper time for a particle going along this whirl line from this initial point to that final point. Okay, so those are the two things that you need to know. All right, so for our problem, we'll choose a very specific path. Okay, so here's x, and again distances are in light years, and time is in years. So okay, again this is also in light years, so but time is in years. Time is in years and this is in light years. Okay, now what we'll do is we stay at home, so this is our whirl line. Okay, the astronaut goes at a speed less than the speed of light, and we are to find that speed, and we'll have him travel at constant speed, and then he gets to the star and then turns around and returns, and he spent 40 years. So the astronaut has spent 40 years okay, and the question is how much time has passed on Earth. Okay, I guess I'll have to fix this diagram. me fix the entire thing. Okay, so there's our axis back, and let's use this. So here's the astronaut's path. Okay, and he goes to the planet, and of course this distance is 20 light years away. This star is. Okay, and here's the world line for a person who stayed on Earth. Okay, and what we have to find is what is the time that elapses on Earth, and we are told that the proper time for this path is 40 years. Okay, and the astronaut goes at constant velocity and returns at constant velocity. So this, of course, is TH by 2, C times that. That's half the time of when TH. Okay, let's see TH. Okay, so now let's calculate the proper time for the astronaut. The proper time for okay, so we'll call the proper time for the astronaut as tau A. Okay, so the interval for the astronaut will calculate this interval on his outward journey. Okay, the interval for the astronaut um, dsa square is delta x square minus c. The interval between these 2 points is this square plus this square. Okay, or this square plus that square is delta x square, which is 20 light years, and CTH by 2 square. Okay, and this, of course, is the proper time for the astronaut. Okay, so what we have is C tau A by 2 square is equal to CTH by 2 square minus delta x square. Now tau A, the astronaut spends 40 years on the journey, and C, remember, is 1 light year per year. So plugging all that in, tau A by 2 is 20, so 20 square is equal to CTH by 2 square, and the distance to the star was 20 light years. So, and again, remember, when you multiply these two, this is in light years, so all the units are 20 light years square. Okay, and so what we have is this is 400 and that's 400, so that's 800. CTH by 2 square is 800 light years square. All right, so CTH by 2 is square root of 800 light year. Okay. So TH is 2 square root of 800 years. C was 1 light year. So, and this should, let's see, what does this work out to? And this works out to 56.6 years. Okay. So what we have solved for is, okay. So what this problem says is the astronauts went on a journey that was to a star that was to a planet that was 20 light years away along this path, and the time that passed on Earth is 56.6 years. So the astronaut themselves age 40 years, and if you stayed back on Earth, you age 56.6 years. Okay. Now let's calculate the speed at which the astronauts went. Okay. So here was the track, and so here's time passing on Earth. This is okay, and so the slope of this line is VT. Okay. So the distance the astronauts traveled was 20 light years. Okay, so distance traveled by the astronaut is the speed at which they traveled times the time that passed on Earth. The speed, according to us, was 20 light years. And speed times time. The time that has passed on Earth is 56.6 56.6 divided by 2 years. So the speed is the speed of the astronauts is 40 divided by light years divided by 56.6 years. Okay. Clear. 40. And that is 0.707 light years per year. Okay. And in these units, remember the speed of light was 1 light year per year. Okay, so beta, which is V over C, is 0.707. So the astronauts traveled at 71% the speed of light. Okay, that